Sun is the closest star to Earth. Even at a distance of 150 kilometers, 93 million miles, its gravitational pull holds the planet in orbit. It radiates light and heat, or solar energy, which makes it possible for life to exist on Earth. Plants need sunlight to grow. Animals, including humans, need plants for food and the oxygen they produce. Without heat from the sun, Earth would freeze. There would be no winds, ocean currents, or clouds to transport water. Solar energy has existed as long as the sun, about 5 billion years. While people have not been around that long, they have been using solar energy in a variety of ways for thousands of years. Solar energy is essential to agriculture, cultivating land, producing crops, and raising livestock. Developed about 10,000 years ago, agriculture had a key role in the rise of civilization. Solar techniques such as crop rotation increased harvests. Drying food using sun and wind prevented crops from spoiling. This surplus of food allowed for denser populations and structured societies. Science, even by reputable practitioners, proceeds in fits, starts, and frequent excursions down blind alleys. As an example, in 1877, astronomers on both sides of the Atlantic observed things about Mars that had the potential for making SETI a done deal. In that year, the red planet had orbited into a particularly favorable opposition, bringing it closer to Earth than is almost ever the case, and making it a tempting target for new discoveries. In Italy, Giovanni Schiaparelli, director of Milan's Berea Observatory, thought he saw linear features furrowing Mars's russet face. His discovery was made using a telescope that is dwarfed by many amateur instruments today. Its objective lens was a modest 8 inches in diameter. Schiaparelli provocatively referred to the features as canali, an ambiguous word choice that would keep eyeballs enthusiastically pressed against eyepieces for a half-century. It was the American astronomer, Percival Lowell, who dug Schiaparelli's work the most. He figured that the canali was deliberate constructions, and he soon became the most literate advocate for the existence of a globe-girdling irrigation system on Mars. This spiderweb of canals was, Lowell averred, the engineering work of advanced beings whose homes were a mere 35 million miles from our own. Ever since the Mariner 4 space mission in 1965, we've known that the canals mapped by these two astronomers, every single one, were optical illusions. Nonetheless, Lowell, who died during the First World War, remained convinced to the end that he had charted the infrastructure of a vast hydraulic civilization. It's noteworthy that the public only showed intermittent interest in Lowell's claims. It's also stupefying to contemplate how different our lives would be today if they had been true. Merely a few weeks before Schiaparelli's work was made public, an astronomer at the United States Naval Observatory in Washington announced a different discovery about Mars, one that would, eventually, also suggest the presence of nearby intelligence. Asaph Hall, using what was then the world's largest telescope, its lens was 3 times the diameter of Schiaparelli's, found 2 midget moons orbiting the red planet. They're so small, you could walk around either one in a day. This was, of course, an interesting story, since moons accompanying planets of the inner solar system are as rare as Swiss jokes. Mercury doesn't have any, nor does Venus. So a pair of satellites around Mars was a compelling astronomical discovery. The Washington Evening Star hailed the find as glorious news from the skies. Following a suggestion from Eton scholar Henry Maiden, Hall christened his diminutive discoveries Deimos, dread, and Phobos, fear. According to the Iliad, these were the 2 bad boy sons of Mars, Ares in the Greek tradition, and Aphrodite, nice names for dead rocks. A lifetime later, something funny happened. Long-term measurements of the inner of the 2 moons, Phobos, showed that it was losing altitude, about 10 feet per century. Its orbit was gradually decaying, much the way a low Earth orbit satellite would gently spiral downward toward the delicate drag of residual atmosphere several hundred miles up. In the wake of Sputnik, this analogy proved irresistible to some, in particular to Losov Shalatsky, a Soviet astrophysicist. In 1958, Skolowski worked the numbers, making estimates of the amount of Martian atmosphere at the altitude of Phobos' orbit. He concluded that the drag on this moon could produce the observed rate of descent only if Phobos was a featherweight, a hollow metal sphere with skin only a few inches thick. That was an astonishing claim, and remember that Skolowski was no dummy. His book a few years later, Intelligent Life in the Universe, enlarged and edited by Carl Sagan, was the first to comprehensively address the question of sentient cosmic life. It was an early guide book for SETI research, but what Skolowski was saying, and what others, including President Eisenhower's science advisor, believed was that Phobos wasn't dead rock at all, but a space station welded together by advanced beings from a star system far, far away. The public, to its credit, didn't riot in the streets at the prospect of an alien outpost nearby. And indeed, a dozen years later, researchers found that the descent of Phobos had been seriously overestimated, and its orbital change was most likely due to tidal friction with the red planet, not atmospheric drag. A credentialed astronomer had falsely hailed a hollow world, but at least it was a mistake with precedent. At the end of the 18th century, Edmund Halley, no astronomical slouch himself, wrote a paper for the Royal Astronomical Society in which he claimed that the Earth was hollow. More precisely, he envisioned that our world consisted of 3 spherical shells surrounding a small, hard central ball, a construction that he reckoned could explain the observed changes in Earth's magnetic field. Indeed, according to Sir Edmund, not only were there massive amounts of Lebensraum beneath our feet, but he suggested that these inner sanctums might even be inhabited. The idea of a vastly void within the Earth is still popular among some people. None of these are geophysicists. Now, the peculiar thing is that, despite the airs of the past, artificial, hollow inhabitants remain a possibility for punitive aliens. In 1959, only a year after Skolowski's speculations about Phobos, British physicist Freeman Dyson reasoned as follows. Since we seem to have an insatiable hunger for energy, it makes sense to assume that aliens have the same. To satisfy their craving for kilowatt hours, extraterrestrials, who are centuries more advanced than we are, will surround their sun with an orbiting flotilla of solar cells, allowing them to capture a large fraction of a star's energy output. It's become popular to envision Dyson's concept as a closed, complete energy-collecting shell around a star, perhaps built with the materials obtained by dismantling an outer planet, a so-called Dyson sphere. However, a complete spherical shell has dynamical and structural problems and is impractical. Dyson himself was thinking more along the lines of a very large number of individual solar collectors. Finding a Dyson sphere, or more realistically a Dyson swarm, would be just about as exciting as learning that Phobos was built of steel plates. It would tell us that someone out there has developed some pretty advanced technology. We can hope to see any of these solar collectors on steroids directly, but they might be uncovered by their waste heat, which would be radiated into space as infrared light. In the last dozen years or so, there have been several attempts to find such objects, usually by mining data from the Infrared Astronomical Satellite, IRAS, that mapped the sky in the 1980s. Living high on the energy hog with a surrounding shell of hardware, it's an intriguing idea, although, given our limited understanding of what advanced societies will do, it might be just another blind alley. Still, science proceeds by looking, and some researchers have. So far, no Dyson. There are some challenges with solar power. First, it is intermittent, or not continuous. When there is no sun, at night, for example, power cannot be generated. In order to provide continuous power, either storage or other energy sources such as wind power must be used. Second, while both photovoltaic and concentrating solar power can be used virtually anywhere, the equipment they require takes up a lot of space. Installation, except for existing structures, can have a negative impact on the ecosystem by displacing plants and wildlife. Lastly, the cost to collect, convert, and store solar power is very high. However, as technological advancements are made and demand rises, the costs are dropping. Fossil fuels such as coal, oil, and natural gas currently produce most of our electric and engine power. They also produce almost all of our pollution. Plus, they are non-renewable, meaning there is a limited supply. The sun, on the other hand, offers free and clean energy in abundance. In fact, it gives much more energy than we can ever possibly use. The only questions are how and when we will take full advantage of it.